Hello student, good morning. I am Dr. Ajay Kumar Sinha, Professor of Chemistry. Today I am going to discuss vapor pressure of solution of solids in liquids. Vapor pressure of solutions of solids in liquids. Last class I have discussed vapor pressure of solution in means a solute was a solution and solvent was solute was liquid and this solvent was also liquid. Solute and solvent both were liquid. Then now I am going to discuss that vapor pressure of solution of solids in liquids. Last class it was liquids in liquids. Today I am going to discuss solids in liquids. This is a common. But before going to this, one a small point I want to just discuss that Rawls law. Yesterday I discussed Rawls law as a special case of Henry's law. Henry's law. Both are similar. Then Henry's law was this P is equal to KH into X, means mole fraction. KH was a constant. Rawls law, constant KH. Then P is equal to KH into X, means mole fraction. And this Rawls law is P is equal to P1 naught into X1. Then see similarity is there. Rawls law is P1 is equal to P1 naught, means vapor pressure of pure solvent, into X1, means mole fraction of one component. Okay, one means one component. And here Henry's law is P is equal to KH into mole fraction. Then see the similarity. Rawls law is P. There also vapor pressure is there. Here also vapor pressure is there. Rawls law, vapor pressure is equal to, means P1 is equal to X1 into P1 naught. Here also P is equal to X is there, means mole fraction. Mole fraction is common in both. Vapor pressure is common in both. Where they are differing, then Henry's law KH is there, constant. And here P1 naught 0 is the just like a constant, pure vapor, you can say vapor pressure of pure solvent, that is fixed. Then see, both are similar. Rawls law and Henry's laws are, you can say, similar. That's why it is called a special case of Rawls law is a special case of Henry's law. These two equation means Rawls law and Henry's law. If we will compare, then what we will get? If compare, then this equations for Rawls law and Henry's law, it can be seen that partial pressure, both are the pressure. The partial pressure of volatile component or gas is directly proportional to the mole fraction in both cases. And in one case, in Rawls law, that is directly proportional to mole fraction. Then if you equate, when you will bring it to the equality, then one constant is required. You have to multiply with that constant. That is the P1 0 in Rawls law. And here in Henry's law, P is directly proportional to X. Both are directly proportional to X. Both. But in Rawls law, that constant is called vapor pressure of pure solvent. And here constant is called KH. Henry's law constant. Okay, that's why it is called this Raoult's law is called as a special case of Henry's law. This I have discussed. Okay, they mean both equations differ only in constant. That is the only things. Now I am going to discuss vapor pressure of solutions. Vapor pressure of solution of solids in liquids. Solids in liquids. This is a common, generally solid is dissolved in liquids. Okay. Then here you have to understand more things, because this here you will understand, then this other things you will understand, means ideal solution, non-ideal solution, all things you will understand. Even elevation in boiling point you will understand. Okay, three things you will understand: ideal solution, non-ideal solution, elevation in boiling point. Hence, just you try to understand vapor pressure of solutions of solids in liquids. Then here this is important class of solution. This solution is of important class. This is the important class of solution, consists of a solid dissolved in liquid. For example, sodium chloride, glucose, urea and cane sugar in water. This is the example. Sodium chloride you can dissolve in water. Glucose you can dissolve in water. Urea you can dissolve in water. Cane sugar, simple sugar, what you are telling, cane sugar in water. This is the example of solid in solid in liquid. And other example, iodine and sulfur dissolved in carbon disulfide. Iodine is solid, sulfur is also solid. Then it can be dissolved in carbon disulfide. Carbon CS2, carbon disulfide. This is also example of solid in solvent, because carbon disulfide is liquid, iodine and sulfur is solid. Some physical properties of these solutions are quite different from those of pure solvent. Okay, here is the important things. Physical properties of these solutions, what I have told now, these solutions are quite different from those of pure solvent. Pure solvent property is different and solution properties is different, because solute plus a solvent. And solute properties is different, solvent properties is different, but when both you will mix, then it will become solution, then its properties will be different from pure solvent. Okay, every pure solvent has their you can say own vapor pressure. After mixing solid, their vapor pressure will decrease. If suppose you have taken water, pure solvent you have taken, distilled water you have taken, pure solvent, then any solvent, its vapor pressure will be highest. Always pure solvents vapor pressure will be highest. And if you will mix in that solute, then its vapor, then that time vapor pressure will be less after mixing. If you will not mix, only water is there, pure water, distilled water, then only its vapor will be there. Above the surface of water, only water vapor will be there, no other things. Freely they are going to it is escaping to the, you can say, atmosphere. But if you will cover it in a vessel, then it will be within the vessel only, but above the surface of water. Suppose it is a covered, closed vessel, then vapor will be inside only, above the surface. Okay, but now suppose you have dissolved some some solid. I have given so much example. Okay, any solid, as for example, sodium chloride, you have mixed in this water. Then now what will happen? Sodium chloride is non-volatile. Non-volatile, correct? Then what will happen in comparison? This sodium chloride is non-volatile. But water, it is somewhat volatile, means because its vapor will come. Always evaporation takes place. Keep in mind, evaporation takes place at all temperature, but their rate will be different. At room temperature, rate will be less, but if you will heat, the rate of evaporation will increase. Okay. Then here at room temperature also water will evaporate, but now it is in a closed vessel. Then that vapor will be inside only. Okay, above the water surface. But if you will mix the non-volatile solid like sugar, NaCl, if you will mix, then what will happen? Then what you will find now, vapor pressure of pure solvent decreased above the surface of water. Now suppose 1,000, just simple example, 1,000 molecules were there, water molecules, H2O, 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 1,000 was there. Just simply for example I am telling you, maybe lakhs, more than that also. Then this suppose 1,000 number was there, H2O in 1,000 number was there. But after adding solute, maybe NaCl, maybe sugar, maybe urea, anything, suppose any one you have added, then now what will happen? Water vapor, their number will decrease. Now this H2O, which was in 1,000 number, now it will decrease. It may become 400, 500, like that. Their vapor will decrease. When vapor will decrease, then vapor pressure will decrease. If a vapor is more, then it will apply pressure on the water surface. Then more the vapor, means more the number of particles, more the pressure. Less the particles, less the pressure. Then now question arises, why decreased? Why vapor pressure decreased? This is the question. You can think, some student may think that NaCl, they have added, or sucrose, or these things, any other non-volatile they have added, then it should increase. It should increase. They can think. But don't forget, you have added non-volatile. Non-volatile, they can't come up. They can't come up. They will be only in the solution. Then now question is that why vapor pressure decreased or decreases? Then it's a simple explanation is there. Easily you can understand. Suppose in a room, door is there, and also you consider from that door 3 persons at a time can enter. Okay, 3 persons. But now you just think that in the beginning 3 members easily can come out from the door. Outside, it can come from the door. But now you consider, then if on the door 2 persons are standing just only on the door, and 3 persons wants to come out, then what will happen? 3 persons wanted to come out, and two persons are standing on the door, then what will happen? Will 3 persons will come out? No, they will face problem. And they can come out, but with difficulty they will come out. Okay, they have to adjust here and there some things. Then same situation is here. In the beginning, water vapor was coming freely to the, you can say, upside in the container. Okay, but now this NaCl, it is solid. It will block the path. It will block the path of water vapors which was coming out. Now just they are covering near the door that situation, that NaCl, some particles which are non-volatile, they will come after dissolving, it will come near the, you can say, surface of water. Then it will block the path of water molecules. They are not able to come freely. Limited number of water molecule will come out, because these NaCl or sugar molecules, it has blocked the path. It is creating problem for the water molecules to come out. That's why now less number of H2O will come out. Then less number of H2O will come out means less vapor will be there. Less vapor will be there means less vapor pressure it will create in comparison to the, you can say, beginning. Then beginning situation is known as pure solvent condition. Pure solvent. Now I give an example for water. It may be other liquid also, any other liquid. Then alone, if only that liquid is there, that is called solvent. But now if you will mix in this non-volatile salt, then now that vapor pressure which was coming easily, freely, now restricted way it will come, and there vapor will be less, number of molecules will be less, and pressure will be less. It will create less pressure on the surface of water. Correct? Then what is the difference between the two? Suppose in the beginning 1000 was there. 1000 unit you can consider. 1000. Now it became 600. After adding solid, now vapor pressure became 600. Just simply you consider. Then delta P, what is the change in delta P? Change in pressure, vapor pressure. Then 1000 minus 600. That is a 400 difference in pressure. Okay, pressure unit may be bar or anything, atmospheric pressure. This is a simple example. Then this is the pressure difference due to, you can say, non-volatile particle. Now that has dissolved. Particle has dissolved, solid particle. But they are covering the path of the, you can say, water molecules which was coming out. That's why solution always has less vapor pressure in comparison to the solvent, means pure solvent. Pure solvent always will have maximum, highest vapor pressure, and solution has less vapor pressure. These things you keep in mind. Very, very important concept I have told you. Now I will go little details. Okay. Now this effect of temperature. Okay. For example, vapor pressure. Already I have discussed. Vapor pressure, actually what will happen, then water will go, and again water will go in the form of vapor upside. Again some water may come down. Then it will maintain equilibrium. Okay. Then here I was discussing that liquids at a given temperature vaporize. Liquids at a given temperature vaporize, and under the equilibrium condition, the pressure exerted by the vapors on liquid over the liquid phase is called vapor pressure. Okay, already I have briefed you that vapors on the liquid over the liquid phase is called vapor pressure. In a pure liquid, the entire surface is occupied by the molecules of the liquid. If a non-volatile solute is added to a solvent in a given solution, the vapor pressure of the solution is solely from the solvent alone. Okay. The vapor pressure of the solution at a given temperature is found to be lower than the vapor pressure of the pure solvent at the same temperature. Correct? That because whatever pressure is there after adding the any solute, that is only due to the solvent molecule only. In the solution both are there, solute plus solvent, but solute is not creating any pressure. Pressure is only due to vapor pressure is only due to the solvent, because solute is non-volatile at the same temperature. In the solution, the surface has the surface has both solute and solvent molecules. Thereby, fraction of surface covered by the solvent molecules gets reduced due to the non-volatile. Okay. In the beginning, their volume was more of open surface upside. Fraction, you can say, fraction of the surface covered by the solvent molecules gets reduced, because on that surface in the beginning only H2O was present, but now some NaCl will be also on the surface. That's why only less number of H2O molecule will come out. Consequently, the number of solvent molecules escaping from the surface is correspondingly reduced. Thus, the vapor pressure is also reduced. The decrease in vapor pressure of solvent depends on the quantity of non-volatile solute present in the solution. If it is more, non-volatile quantity is more, then vapor pressure will be further less. The decrease in the vapor pressure of solvent depends on the quantity of non-volatile solute present in the solution. Irrespective of its nature has no meaning here. For example, decrease in the vapor pressure of water by adding 1 mole of sucrose, means sugar, in 1 kg of water. 1 mole sucrose you have added, ordinary sugar, in 1 kg of water is nearly similar to that produced by adding 1 mole of urea to the same quantity of water at the same temperature. In 1 beaker you have taken 1 liter water, other beaker also 1 liter water. In one you have added urea 1 mole, and in other 1 mole sucrose. Then vapor pressure will be the same. It means it does not depend upon the nature of solute. One is urea, other is sucrose. Correct? Then urea is different, and sucrose is different, but in vapor pressure both are 1 mole. Hence it will not depend upon the pressure. Vapor pressure does not depend upon the nature of solute. This is a very, very important things I have discussed. Temperature is same, despite that same temperature, same volume of the solvent, and solute also 1 mole you have added. Then there is no change in this vapor pressure. Okay. Now Raoult's law in its general form can be stated as, how you can statement? Then I am telling you this, you remember. For any solution, the partial vapor pressure of each volatile component, not a non-volatile, each volatile component in the solution is directly proportional to the mole fraction. What we have discussed, same things. P is direct, vapor pressure is directly proportional to the mole fraction. Here they say if we convert the equality, then that constant will be known as, I can say, P0. P0 means vapor pressure of pure solvent. Vapor pressure of pure solvent, P0 or P0, whatever I am telling you. This is the proportionality constant, but known as this vapor pressure of pure solvent when you have not mixed the solute that time. Okay, always it will be greater than solution. Then this is the actually Raoult's law. Again I am telling you, for any solution, the partial vapor pressure, P only you can consider, partial vapor pressure of each volatile component in the solution is directly proportional to the mole fraction. Correct? In a binary solution, now you are knowing two solutions, solute and solvent, two phase. In a binary solution, let us denote the solvent 1 and solute by 2. So solvent you consider 1 and solute 2. When the solute is non-volatile, only the solvent molecule are present in the vapor phase, because that is the non-volatile. Okay. When the solute is non-volatile, only the solvent molecules are present in the vapor phase and contribute to vapor pressure. Now this by graph also you can understand. Already last class I have sent, similar graph is there. Last class I have sent. Then here that vapor pressure versus mole fraction. Vapor pressure versus mole fraction. X-axis mole fraction, y-axis vapor pressure. You will get a straight line. The vapor pressure of the solvent, okay, that suppose P is the vapor pressure, P1 is the vapor pressure of solvent, and X1 be the mole fraction, and P1 0 means P1 not be the vapor pressure of the pure state, means pure solvent. Then according to the Raoult's law, you can tell that P1 is directly proportional to X1. P1 is directly proportional to X1, and then convert it into the equality. Then P1 is equal to P1 not 0 into X1. The proportionality constant is equal to the vapor pressure of pure solvent, that you are denoting by P1 naught or P1 0, or upside subscript 0 you can write. Then P1 is equal to X1 into P1 naught 0. This is the mathematical statement of Raoult's law. This is very, very important, and a plot between the vapor pressure and the mole fraction of the solvent is linear. Now I am discussing these things. Ideal solution. Actually, liquid solutions can be classified into ideal and non-ideal solution on the basis of Raoult's law. Okay, the important thing, liquid solution, both are liquids. Both are liquids. In liquid solution, both are liquids. Then can be classified into ideal and non-ideal solution on the basis of Raoult's law. Then what is the ideal solution? Then in a simple way I am telling you that ideal solution means solution which will can say follow Raoult's law, solution which obeys Raoult's law is called ideal solution, and which does not obey Raoult's law, that is called non-ideal solution. Now I am telling details. The solution which obey Raoult's law over the entire range of concentration, means let low concentration also, high concentration also, are known as ideal solution. The ideal solution have two other important properties. Question is asked. The enthalpy of mixing in the pure components to form the solution is 0. Means if two solution you are mixing, it is a two component, means solute and solvent both are mixing, and here both are liquid. Solute is also liquid, solvent is also liquid. Okay. Then after mixing, temperature should not rise. Temperature of the solution should not rise. Means delta H should be 0. Delta H is equal to 0. Okay. Then this is the first property, that if the solution is ideal, then after mixing two solution, two pure components, suppose you are mixing two pure components, to form a solution, then delta H should be 0, first thing. And now suppose 10 ml plus 10 ml, you have mixed, two components you have mixed, 10 ml each, then it should be 20 ml only, 10 plus 10, 20. It should not be 18 or 19, or it should not be 21, 22, like that. Volume should not change. Means delta V of the solution should be 0. Okay. Or delta, you can say delta V of the mixture. Delta V of the mixture should be 0, or delta H of the mixture. Delta H of the mixture should be 0. Volume also should be 0. Delta V, volume of the mixture should be 0, and enthalpy of the mixture should be 0. Both should be 0. This question is asked. Okay. Then three things I have discussed mainly for main property, ideal solution. What is the ideal solution? I told you, and special properties I told you. Now you can say that here little more in pure components, the intermolecular attractive interaction will be of two types, AA types and BB types. Whereas in the binary solution, in addition to these two interaction, AB type of interaction will also be present. Means now suppose you have mixed two component, you have mixed, correct? Then now suppose component A and component B, component A and component B you have mixed. Then many molecules of A will be there, many molecules of B will be there. A, A and B, there are two components, separate molecules will be there. A one component, B another component. Then A have many molecules, B have many molecules. Then here you can see what will happen, that A molecule, many A molecules are there, then they themselves will interact. They themselves will interact. A molecules, many A molecules are there. Then they will interact among themselves. And B also, all B molecules also, they will interact among themselves. This is the one thing you will remember. A will attack, will you can say interact with A, same molecules. B will interact with same molecules. Correct? That's why it is called AA and BB type. Two type. Now third type. What is the third type? Then now A and B, they can also interact. A and B also can interact. Then now its effect you can see. Very interesting. Okay. Actually it was complicated. Now we will understand very easily. Then now these two type of interaction you have seen. Three types you can tell. AA, BB, AA among themselves, BB among themselves, and AB type of interaction. Three types of interaction. These three types of interaction will be also present in the you can say ideal solution. Okay. Then now what will happen, that I am telling you now, that this in binary solution, in addition to the this AA and BB, AB type of interaction will also be present. If the intermolecular attractive forces between the AA and BB are nearly equal to those, if now condition, see here only you have to understand that if the intermolecular attractive forces between the AA and BB are nearly equal to the those between AB, this leads to the formation of ideal solution. Means AA will interact, BB will interact, then this you can say interaction is equal to AA interaction, BB interaction is equal to the AB interaction. Then this is also called ideal solution. Means in ideal solution there is all forces are equal. AA interaction, BB interaction, and AB interaction. A and B also they can interact. Then in this case, in ideal solution, all interactions should be same. Then that solution is called, that banded solution is called ideal solution. Okay. Then very important things now I have told you. Okay. Then this will lead to the formation of ideal solution. And now cases will come. A perfectly ideal solution. First understand only ideal solution. A perfectly ideal solution is rare. It is not common, rare. But some solutions are nearly ideal. Not 100%, 99.9% ideal. They have ideal behavior. They will do ideal behavior. A perfectly ideal solution is rare, but some solutions are nearly ideal in behavior. Example I am telling you. Solution of N-hexane and N-heptane. Hexane means 6, N means normal. N-hexane, N-hexane and N-heptane. Heptane means 7. Then both are ideal solution. Means they will behave ideally. First example, normal hexane and normal heptane, binary. Okay, binary solution. Second, bromoethane and chloroethane. Bromoethane and chloroethane, they also behave ideally. Third example, benzene and toluene. Benzene and toluene all falls into this category, means ideal solution. Here many questions are asked on this concept. Here you should think by seeing a structure also you can tell if two structures are almost equal, 99% equal, then if both are soluble to each other, then both will make a ideal solution. If both components have similar type of a structure and they are soluble, if they are soluble, mixing, okay, if they are soluble, then obviously because a structure will be the almost same, hence they automatically like dissolves like, they will make ideal solution. Then three examples I have told you, benzene and toluene. Also you will see the structure benzene C6H6 and other is C6H5 and CH3 is attached. And similar, normal heptane, normal hexane. Then hexane and heptane, only one hydrogen, only one carbon difference is there. Correct? Hexane means 6 and heptane means 7 carbon. 6 carbon, 7 carbon, almost same. Hence, if we will mix this pair, these components, these two components, three example I told, then all will make a ideal solution. Question is asked, example they will ask. Okay. Then again I am telling you, keep in mind, and if you have notebook and pencil or pen, you can write down also. First example is that normal hexane and normal heptane. First example. Second example is bromomethane and chloromethane. And third example is benzene and toluene. Okay. Benzene and toluene. Now I am discussing non-ideal solution. Non-ideal solution. Already I told you, when a solution does not obey Raoult's law over the entire range of concentration, then it is called non-ideal solution. The vapor pressure of such a solution is either higher or lower than the predicted by Raoult's law. What was these things? In Raoult's law you have seen delta H was 0, delta V was 0, delta V mixture, delta H of mixture was 0, delta V of the mixture was 0 and interaction was same. But here nothing will match. Either it will be more or less. Either they will be more or less. Value will be not 0, maybe less or maybe more. Means they will not follow Raoult's law. Then that's why it is called non-ideal solution. Okay, the vapor pressure of such a solution is either higher or lower than that predicted by Raoult's law. If it is higher, if condition they see, listen carefully, if it is higher, the solution exhibits a positive deviation. Positive deviation. If it is higher, means vapor pressure is higher than what was predicted by Raoult's law, the solution exhibits positive deviation, and if it is lower, it exhibits negative deviation from Raoult's law. The plot of vapor pressure, I will try to send it. The plot of vapor pressure as a function of mole fraction for such solution. This graph plots, you can tell, graph that I will send, but it is very easy to understand. Last class I have discussed that with the mole fraction, vapor pressure depends on the mole fraction. From high to low slowly, and if mole fraction will decrease, then pressure will become less, finally zero. Right angle triangle it is forming, correct? And if it will increase, if mole fraction will increase, then again vapor pressure will increase, and it will go to the maximum. In this case also it forms a right angle triangle. Then if you will take a solvent and a solute, then one will be whose vapor pressure is less, that will be automatically, that will be solute, because large quantity is considered as a solvent. Large quantity, the large quantity, if solvent is more, then obviously pressure will be more. Then solvent will show more vapor pressure and solid will show less vapor pressure. Then if you will this vapor pressure of solute, maximum vapor pressure of solute and maximum vapor pressure of solvent, if you will join, then that is the it will tell about the total vapor pressure. One line you can draw. Okay, it will look like this situation will be just like this thing. H in a right angle triangle, that type of this, that situation will come. Okay, then the hypotenuse form it will come, hypotenuse. Then this is what you have seen, 3 line you have drawn, maximum vapor pressure of solute, maximum vapor pressure of solvent, that you have joined. And right angle also, when pressure was decreasing, mole fraction was decreasing, vapor pressure was decreasing, then it also taken a shape of this thing's right angle triangle, correct? If you will join this for the solute, highest pressure and lowest pressure means 0, it will be H, hypotenuse. And same way, if mole fraction is increasing for the solvent, as for example, then 0 and highest, if you join, then again it will make right angle triangle. Okay, but it will be opposite to the solute. Just both side perpendicular you can draw. Okay, then this is the case, it is for ideal solution. This is the case for ideal solution. But in non-ideal solution, what will happen, that this will be this, now we are saying H is just like a straight line from you have joined. But now in a non-ideal case, they will differ from this structure. H hypotenuse, you have seen now, there it will differ. They will not follow a straight line. Minor change will be there. That will be less or more. If it is more, then above the hypotenuse, 3 hypotenuses there. 3 hypotenuses there. One for when it was, you can say, decreasing. That time one triangle formed. And other when it was increasing, 2. And third, when you have joined, you can say this highest vapor pressure of solute and highest vapor pressure of solvent, again you have joined. Then these 3 are there. Then all you can say, just like one curve you can write. Every hypotenuse you put a curve. Curve means it is not following the Rolle's law. Line you keep it. 2 type of, one a straight line you can put, other dark line you can put, or dot. One will be dark, the other will be dot. Then it will swell, means it will swelling will be there, just like swallow, that it will be upside, correct, that it is going upside, positive deviation. Then in all three lines, it will go just like that it is swelling is there, like that type of things. Curve, like it will go to make a curve for starting from this highest to 0. One just you can put like that, one curve like that you can put. Then 3 curve will be the upside of the line, upside of the 3 hypotenuse, upside you have drawn and one curve, dot like that, correct. Then 3 curve will be there. Then up, all will be up, because it is a positive deviation. They don't have 0, they have more than 0 value, correct. Then that's why it will be up. And in the negative deviation, same curve you can write down the line. 3 lines are there, hypotenuse, then 3 curve down the line you can put, starting from one point to the other point. Then 3 curve will be there on 3 lines. Then this is the actually diagram. I will try to send it. Then this is the positive deviation and negative deviation. Okay. Then now I have already discussed also these 2 type of graphs, and it is just a mole fraction versus vapor pressure y-axis, mole fraction x-axis. Okay. Then here 2 diagram you will find, one for positive, that swelling will be just like a upside, you can say above the line, and second diagram will be below the line, same type of diagram, but one is above the line, and other diagram it will be below the line. Okay. Then this I have told you about these things, positive and negative, you can say, deviation. Now example you can say that carbon disulfide, that Raoult's law, positive I am already told you, in a solution formed by adding carbon disulfide in acetone, carbon disulfide CH2 in acetone you have added, both are liquid, carbon disulfide and acetone, both are liquid, then it will give a positive deviation, upside. Okay. The dipolar interaction between the solute solvent molecules are weaker. Here again important point you have to understand, why it is swelling is there in this type of curve is there, that I want to tell you. Mixture of ethanol and acetone first understand. Mixture of ethanol and acetone behave in the manner, in this what is showing that vapor pressure of solution in the curved form. In pure ethanol molecules are hydrogen bonded. Very important concept I am telling you, listen carefully. In pure ethanol, C2H5OH, many C2H5OH are there, many. Then molecules are hydrogen bonded in ethanol. All ethanol will be bonded, hydrogen bonding will be there. On adding acetone, this is one type of you can say interaction. On adding acetone, in that acetone you are adding, its molecules get in between the host molecules. Host molecules means it will enter to the ethanol between the ethanol molecules and break some of the hydrogen bond between them. due to this weakening of interaction. This happens due to weakening of interaction. The solution shows positive deviation. Positive deviation because bond has broken. Bond has broken. Then what will happen? Bond has broken, bond become loose. That's why that vapor pressure will be more. Then this curving means going just like swelling situation, that is showing more vapor pressure. Okay. Then this is happening due to the, you can say, interaction between, you can say, AB interaction, you can tell AB interaction. Due to that it is happening positive deviation. Positive deviation from Raoult's law. Okay. In a solution formed by adding carbon disulfide and acetone, the dipole interaction between the solute-solvent molecules are weaker than respective interaction among the solute and solvent molecules. Here, dipole interaction between the solute-solvent molecules are weaker. That's why positive deviation. Weaker than the respective interaction among the solute and solvent. I told you A type, B type. Then they are strong. Hence they are not breaking. A interaction is more, BB interaction is more. That's why it is a bond is not breaking. But AB type, due to AB type means interference is there, interaction is there, then due to that positive deviation took place. Okay. And now a reverse case you can understand. Okay, I will discuss that things also. This solution, this both example I told you. First example I given you ethanol and acetone. Other example I told you, that is the this things. This second example I have told you about the this things. Second example, solute this things. Solution I have second two example I have given. Okay. Then one example, in both example is a positive deviation. Okay. That is second example, carbon dioxide. I told you carbon dioxide in acetone. Carbon disulfide CH2 in acetone. Second example. First example was ethanol in acetone. Acetone is common. Ethanol and acetone and carbon disulfide in acetone. That both are positive deviation. And reasoning is that same reasoning, that AB interaction is more. AB interaction is that due to that AB interaction, weak bonds are there. They will break it. Then more molecules will develop, more vapor will develop. But now I am telling you, in case of negative deviation from Raoult's law, the intermolecular attractive forces between AA and BB are weaker. AA and BB are weaker than those between AB. Okay, and leads to decrease in vapor pressure, resulting in negative deviation. Here just I will compare both positive deviation and negative deviation. Then you understand, then otherwise you will get confused. The cause for this deviation lie in the nature of interaction. Okay. These deviation cause for this deviation lie in the nature of interaction at the molecular level. In case of positive deviation from Raoult's law, AB interactions are weaker. AB interactions are weaker than those of AA and or BB. Okay. In this case, the intermolecular attractive forces between the solute-solvent molecules are weaker than those between the solute-solute and solvent-solvent molecules. This means that in such solution, molecules of A or B will find it easier to escape from the pure state. Okay, AA or BB will find some scope, or will find it easier to escape than in pure state. Okay, it will escape. This will increase the vapor pressure. This will increase the vapor pressure. And now in case of negative deviation from Raoult's law, what will happen? The intermolecular attractive forces between AA and BB are weaker. AA and BB are weaker than those of AB. AB is strong. A and B both it will react, then reaction will be less reaction. A and B, the interaction will be less and leads to decrease the vapor pressure. Means both are not reacting, A and B. That's why vapor pressure will be less. Correct? A and B both are not reacting. Strong is there. Then they will not escape. They will not go to the above the surface. Then when they will not go, vapor will not go to the surface, then they will not create the vapor pressure, or you can say less. Then AB interaction is very, very important. If AB interaction is there, strong, then positive deviation. If AB interaction is more, because the bond they will break it, they will be free. But if they are not reacting, interaction is less, weak, and they are all AA and BB will just it will be there, but interaction is not there. Interaction is not there, then they A and B will be not free. Then vapor pressure will be less. That is called negative deviation. Then AB interaction is very, very important. In positive deviation, AB is weak. AB interaction is weak. Okay. And here AB interaction is more. Then here I have told you that AB interaction is meaningful. Okay. And due to that, positive and negative deviation takes place. Due to weakening of interaction, weak interaction is responsible for positive deviation. Okay. And a strong interaction. Then for the weak interaction, you can say positive deviation, and this strong attractive force between in case of negative deviation from Raoult's law, the intermolecular attractive forces between AA and BP are weaker than those between AB, and leads to decrease in vapor pressure. Okay. Then here AB interaction AB interaction is very, very important. Because AA and BB are weaker and weaker than those of between AB. AB interaction is more. AA and BB are weaker and AB is more. Then if interaction is more, then they will react, they will be not free. They will be not free because both are reacting. That's why this vapor will be less. Decrease in vapor pressure resulting in negative deviation. Okay, AA and BB are weaker than those between AB, and reverse case is with positive. Okay, this I have told you, and this question is basically asked. I told you acetone formula is CH3COCH3. Again another acetone you can take as again CH3. This thing acetone you have taken CH3 COCH3 and chloroform example, suppose you have taken CHCl3, then CHCl3, in that chloroform H is there and acetone CO is there, then both will interact. Okay, then in this case, because interaction is there, then they will when they both will react, then they will be not free, hence it will not go to the you can say above the distant surface. A mixture of chloroform and acetone forms a situation. This is the example of negative deviation. A mixture of chloroform and acetones form a solution with negative deviation from Raoult's law. This is because chloroform molecules is able to form hydrogen bond with acetone molecules. Because bonding is there, the molecules will be heavy. It will not escape. It will not go in the form of vapor. Vapor will be less. Then this I told you this interaction decreases the escaping tendency of molecules for each component, and consequently the vapor pressure decreases, resulting in the negative deviation from Raoult's law. Okay, and when interaction will be less, then they will have a scope for going outside. They can escape. Vapor will be more when interaction is less. And interaction just means they are free, they can go outside. Then positive deviation. If interaction is more, A and B, more, all A and B are reacting, then they are not, then all will you can say react only. They will bind to each other, they become heavy, it can't go. Then vapor pressure will be less. That's why it will show negative deviation. Then here one more thing I want to tell you. Some liquids on mixings form azeotrops. Question is asked. Azeotrops, azeotrops, which are binary. What is this azeotrops? Then azeotrops are binary mixture having the same component in liquid and vapor phase. In both, in vapor phase or liquid phase, same components are there, and that solution is called azeotrops. Azeotrops, what is the azeotrop? Then azeotrops are binary mixtures having the same composition in liquid and vapor phase. In vapor phase also same composition, liquid phase also same composition. vapor phase and liquid phase. That is the characteristic of azeotrop. Always remember same composition in liquid and vapor phase, and boil at a constant temperature. Both will boil at a constant temperature. In such cases, it is not possible to separate, because both are same temperature, both will boil, both will in the same temperature. Then it is not possible to separate the components by fractional distillation. There are two types of azeotrops called minimum boiling azeotrop and maximum boiling azeotrop. Okay, there are two types, minimum and maximum. Raoult's law form, you can say Raoult's law form minimum boiling azeotrop. Raoult's law, minimum boiling azeotrop at a specific temperature. For example, ethanol water mixture obtained by fermentation of sugars, in a factory, okay, or in this lab also fractional distillation you can do. Ethanol water mixtures, generally it is obtained by fermentation of sugars in industry also or in lab also. On fractional distillation, it gives this mixture, azeotropic mixture, ethanol water. Distillation gives a solution containing approximately 95% by volume of ethanol. In this mixture, water and ethanol, 95% ethanol will be there and 5% water will be there. This is azeotrop mixture. Azeotrop means vapor phase, liquid phase, same composition. Once this component, composition that is known as 95 and 5, 95% ethanol by volume, okay, and then this is known as azeotrop composition, and has been you can say this 95% I told you by volumes of ethanol and 5% will be water. This you can't separate. On this composition, actually once when it is you will get this composition 95% alcohol and 5% water. Once this composition known as azeotrop composition has been achieved, the liquid and vapor have the same composition and no further separation occurs. Okay, whatever in the last will be remaining. In the beginning, alcohol you can separate because water is also mixed. Then after that 95% you can separate. After that what will happen? Because both are mixed. It is not like that water is separate, alcohol is separate. Then up to 95% you can separate, and rest 5% you can't separate. In that both are present. Composition is same in phase and liquid phase and gaseous phase, vapor phase. Hence you can't separate and no further separation occurs. The solution that show large negative deviation from Raoult's law form maximum. This was the minimum, what I told you now, ethanol water. That was the maximum. The solution that show large negative deviation. The solution that shows large negative deviation form this large negative deviation from Raoult's law form maximum boiling azeotrop at a specific composition. Nitric example I am telling you, nitric acid and water is an example of this class. That is the maximum boiling azeotrop. Azeotrope shows a large negative. This shows large negative deviation from Raoult's law and maximum boiling point. Maximum boiling point. Correct? Maximum boiling point. This is called actually maximum boiling point azeotrope, and first one was minimum boiling point azeotrope. At a specific composition, nitric acid and water is an example of this class of azeotrope. This azeotrope has the appropriate composition. This azeotrope has a appropriate composition, 68% nitric acid and 32% water by mass, and it boils at a 393.5 Kelvin. 393.5 Kelvin. At this temperature, you will find azeotropic maximum boiling azeotropic you will get, and its nitric acid will be 68% and water will be 32%. You can't separate both. You can't separate percentage. You can know, you are knowing, but separation you can't do because temperature is both have same temperature, same composition in the solution also and in vapor phase also. Then now I am stopping only here. Next class again I will continue. Thank you.